All right, let's dive into the invisible chemistry that honestly runs our entire world, solutions. I mean, from the air we're breathing right now to the coffee in your mug, pretty much everything is a mixture. And if you understand how they work, you start to unlock some really fascinating secrets about, well, everything.
So, let me ask you this. What could possibly connect a can of soda, a scuba diver, and a shriveled up pickle? It sounds like the setup for a terrible joke, I know, but it's actually a real scientific puzzle. And the answer to all of it lies in the chemistry of solutions. So stick with me, and I promise this is all going to make perfect sense. So here's our game plan. We're going to tackle this in 5 simple steps. First, what even is a solution? Then, how do we measure what's in it? After that, we'll get into the fun stuff, gases, pressure, and why your soda fizzes. Then we'll see how it's not what you mix, but how much you mix that matters. And finally, we'll uncover the secret flow of osmosis. Okay, first things first. Before we can get to the divers and the pickles, we have to get a really solid handle on what we're even talking about. What is a solution? At its heart, a solution is just a perfectly smooth mix. Think of it like this. You have 2 main players. The solvent, which is the big boss, the one you have the most of, like water, and then you have the solute, the thing that gets dissolved, like a spoonful of sugar. Once you stir it in, you can't see the little sugar crystals anymore, right? The whole thing is completely uniform. That's what chemists call homogeneous. And here's the thing, we tend to think of solutions as just solids dissolved in liquids, but they are so much more than that. They exist in every state of matter. The air we're breathing, that's a solution of nitrogen, oxygen, and other gases. You can even have solid solutions, like brass, which is basically copper dissolved in gold. The world of mixtures is way more diverse than you'd think. Okay, so we know what a solution is, but in chemistry, just saying something is kinda watery or really concentrated just doesn't cut it. You have to be precise. We need a way to measure exactly how much stuff is in the mix. And chemists have a whole bunch of ways to do this. You've probably seen mass or volume percentages on food labels. Parts per million is awesome when you're talking about tiny amounts, like a pollutant in a river. But in the lab, there are 2 big ones, molarity and molality. Yeah, they sound almost exactly the same, but that one little letter difference is actually a huge deal. So here it is, the key difference. Molarity, with an R, is all about how many moles of stuff you have in 1 liter of the final solution. But molality, with an L, is about how many moles you have per kilogram of just the solvent before you even mixed anything in. So why on earth does that tiny distinction matter so much? Well, it all comes down to temperature. Think about it. If you heat up a liquid, it expands, right? Its volume changes. So its molarity actually changes too. But its mass, the mass never ever changes with temperature. That makes molality completely independent of temperature. So for any experiment where you need absolute precision, molality is your rock-solid go-to measurement. Okay, now we can finally talk about our fizzy soda. To understand what's going on there, we need to dive into this really cool relationship between gases, liquids, and one super important ingredient, pressure. And it's all governed by something called Henry's Law. Basically, what it says is, the more you press down on a gas sitting on top of a liquid, the more of that gas you can force to dissolve into it. Just imagine literally pushing those gas molecules down and cramming them into the liquid with all that pressure. More fizz. It's that direct. And that is exactly what the soda companies are doing. They use Henry's Law to supercharge your drink with carbon dioxide. They sealed that can under crazy high pressure to dissolve as much CO2 in there as possible. And that psst sound when you crack it open, that's all that extra pressure escaping, and the gas immediately starts bubbling out of the solution. But this law isn't just about soda. It can be a matter of life and death. For a scuba diver, the intense pressure deep underwater forces way more nitrogen gas to dissolve into their blood. If they come up to the surface too fast, that pressure is released, and the nitrogen suddenly forms dangerous bubbles inside their body. That's a painful and serious condition called the bends. And the exact opposite happens up on a high mountain. The air pressure is lower, so less oxygen dissolves in your blood, which can make you feel weak and confused. So next up, we're going to look at a really weird set of properties where the type of thing you dissolve doesn't matter at all. It's not about what the particle is, it's just about how many of them there are. These are called colligative properties. Now, this is a wild idea. It means that if you dissolve, say, 1,000,000 salt particles in water and 1,000,000 sugar particles in another beaker of water, the effect on these specific properties will be exactly the same. The water doesn't care that one is salt and one is sugar. It just knows that there's a particle there taking up space and getting in the way. The first of these properties is something called vapor pressure. Imagine the surface of the water is like an exit door. In pure water, it's just water molecules lined up, ready to evaporate and escape. But when you add a solute, like salt, those salt particles just hang out at the surface, acting like big, clunky blockers at the door. They make it harder for the water molecules to get out, which means the vapor pressure goes down. And that one simple fact directly leads to two other things we see all the time. Because it's harder for the water molecules to escape, you now have to heat the solution to a higher temperature to get it to boil. And, for kind of the same reason, you have to cool it down to a lower temperature to get it to freeze. This is literally why we throw salt on icy roads. It lowers the freezing point of water and makes the ice melt, even when it's below freezing outside. And here we are, our final section, the one that holds the secret to our poor, shriveled pickle. We're talking about the incredible process of osmosis, this silent, constant flow that pretty much makes life itself possible. Okay, let's break that definition down. Imagine you have a special wall, a semi-permeable membrane that only lets the small water molecules through but blocks bigger things like salt. Now, if you have really diluted water on one side and super salty water on the other, the water molecules will automatically flow from the diluted side over to the salty side, trying to even things out. Nature loves balance, and osmosis is water's way of trying to restore it. And that explains our pickle. A cucumber is full of water. When you toss it into a jar of super salty brine, the concentration of salt is way higher outside the cucumber than inside. So to try and balance things out, water rushes out of the cucumber and into the brine. And what happens? It shrivels up. That's osmosis in action. This process is absolutely critical for our bodies. Our red blood cells have to live in what's called an isotonic solution, where the salt concentration inside and outside the cell is perfectly balanced. If you were to put them in a hypertonic or extra salty solution, water would rush out and they'd shrivel up. Put them in a hypotonic solution, like pure water, and water rushes in so fast that they can swell up and actually burst. But what if we could flip this whole process on its head? What if we could hijack osmosis? Well, that's exactly what reverse osmosis is. We know that water wants to flow towards the saltier side, but what if we apply a ton of pressure to that salty side and physically push the water back the other way, against its natural flow? Well, doing that leads to one of the most powerful technologies we have: desalinization. We can take incredibly salty seawater, apply immense pressure, and literally squeeze pure, fresh H2O through a membrane, leaving all the salt and other gunk behind. It's how we create fresh, clean drinking water from the ocean itself. So from the fizz in your soda to the reason divers get the bends to how we can literally create fresh water from the sea, it's all the chemistry of solutions. We figured out how to use pressure and concentration to do some amazing things. So it really makes you wonder, if we can master this fundamental flow to solve a problem as big as water scarcity, what other massive challenges could we take?
This chapter is very important for your board exams, so revise it well. Like this video, subscribe to my YouTube channel, and keep learning smart. We meet in next videos. Thank you.